All right, so the third step is you need to add up all the pieces. And this will get you to the analytical solution for the electric field of that shape, and this is also where we typically integrate. Not always. Sometimes it's a really straightforward addition. And once you're all done and you have your solution, you need to double check that it makes conceptual sense. Is it going in the right direction? Do the positives and minus signs make sense? And also, you always want to check the units. You should have newtons per coulomb. All right, so now that we know our strategy, let's go back to our thin rod. Okay, so step one, we want to divide and conquer. So by this, we want to break it up into little manageable pieces that we already know how to calculate. I mean, this is all about making stuff easier, not harder. We don't want to do something we don't know how to do. We want to do something we do. Okay, so we're going to be observing at the middle of the rod. So here is our observation location. We're going to say this is an X, and our rod is right here in Y. And so all of these little delta Y's for the different places will all have some fraction of the total charge. Okay, so there's a couple things we're going to be assuming. We're going to assume a very skinny rod. So infinitely thin, thickness negligible. And we're going to assume chunks small enough to be point charges. And this is, of course, because we already know how to calculate point charges. So we want to get this into something we can calculate that is reasonable for the shape. So we're just basically going to have a big, long string of point charges. So for step two, we want to choose some axes that make sense and then start to get some little delta E's that we can start adding together. So I'm going to go ahead and draw on this picture. It makes sense to set the origin right at the middle of the rod. We're going to have this be an X and this an Y. Those are reasonable axes to set. Okay, so moving on to go after expressions for delta E. We have our easy origins. And so we're going to have a field from X in that direction. We're going to have a field from Y in that direction. And then our delta E's will point along our R vector. And of course, this is going to this setup will depend on what piece we are looking at. So R will point from our piece to the observation location. So for this particular setup, we are observing in X, and we are summing in Y. So this is sum Y, giving us an R of X minus Y, 0. And then the magnitude of R, since we'll need that for the electric field equation, is then X squared plus minus Y quantity squared to the power of 1/2, and then R hat is equal to R over R magnitude, which is x minus y and 0, divided by x squared plus minus y squared, all to the power of 1/2. And that's as simple as you can make those expressions for r magnitude and r hat. And of course, all of this is because we want those little chunks of delta E equations. Okay, so now that we have all the goods to get it into a vector, we want to look at the scalar component of the electric field. So remember, the scalar component is not the magnitude because it can be positive or negative. It's what's scaling the field to give you the amount of it, whereas this is telling you what direction it's going in. It's giving it the three-dimensional aspect of it. So we have 1 over 4 pi epsilon naught delta Q for our point charge over r squared. We do have an expression for r right here, so we can put that into our r squared, and we can see that this becomes 1 over 4 pi epsilon naught delta Q over x squared plus minus y squared. And now that to the power of 1/2 has gone away since the 1/2 canceled out the squared here. Okay, so now we need to expand this into a delta E vector. To go after the x and y components. It's easier unless you want to do multivariable integration, which is fine. We want to break these up into x and y components. So E is equal to 1 over 4 pi epsilon naught delta Q over x squared plus minus y squared times x minus y 0 divided by x squared plus minus y squared to the 1/2. And so basically we're going to break out this part and this part. So we're going to have two components for the delta E's. We've got two of the same taken to two different exponents. We can add those exponents together, just condense this down. Delta E is equal to 1 over 4 pi epsilon naught delta Q over x squared plus y squared to the 3/2 times x minus y and 0. And then it follows that we would have an expression for delta E in x of 1 over 4 pi epsilon naught x times delta Q over x squared plus y squared to the 3/2, and delta EY is equal to 1 over 4 pi epsilon naught minus y delta Q over x squared plus y squared to the 3/2, and then delta EZ is 0, which you would predict from looking at our original picture. Okay, so in order to get this into a formula that can be summed over, we still need to deal with this delta Q. We have no means of putting it into terms that are meaningful for other selections. So we know the rod has uniform charge. And so delta Q is going to be delta Y over the length of the entire rod. So that's going to get us the percentage of our chunk times the total charge. If you're worried about units, those meters will cancel each other out. Okay, so now we have a relationship for delta Q in terms of the delta Y that we're choosing, the length which we know and the total charge that we know. All right, so we can use this to rewrite our little energy equation. So delta EX becomes 1 over 4 pi epsilon naught Q over L times X over X squared plus Y squared times 3/2 times delta Y. This is very useful because we will end up summing over delta Y. This is going to be what's changing. And delta EY is equal to 1 over 4 pi epsilon naught Q over L minus Y over X squared plus Y squared to the 3/2 times delta y. So now we have both expressions in terms of our actual varying component, which is y, and this concludes step 2. That's what you want to get to. Okay, so now we want to move on to step 3 where we add them all up. And you'll see in step 3 the benefits of some of the choices we made. So we have our rod that we're going to be adding, and we can just kind of verify something by real quick visual inspection. So we've got 2 little delta y's corresponding to either end. Here they are. So we're going to have, we'll call this one 2, call this one 1. And so we have delta E1 and delta E2 here. And these will sum together, giving us delta E1 plus 1 plus delta E2 only in x. And so what we can see is for every component on the top, there's one on the bottom that is opposite. So our expression for the electric field of this wire is only going to be in x. We can see this from this inspection. We can also see that from our original picture where we just drew the field only coming out symmetrically from the wire. So again, this is all starting to make sense, and also this is the beauty of why we chose our coordinate points to be what they are. We want to make our lives easier, not harder. Okay, so let's do some math. So each delta Q contributes delta EX to the net electric field. So, and basically when we're dealing with E net, it's equal to E delta EXY1 plus delta EXY2 dot, 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 dot. So delta E in X is going to be the sum of all of the little delta EX's. This is equal to 1 over 4 pi epsilon naught Q over L times X over X squared plus Y squared to the power of 3/2 times delta Y, just plugging in our expression that we'd previously derived. And delta EY is equal to the sum of all of our little delta EY's, which is equal to 1 over 4 pi epsilon naught Q over L minus Y over X squared plus Y squared to the 3/2 times delta Y. Now, when you do a sum, you can pull your constants out in front. So I'll do that now for delta EX is equal to 1 over 4 pi epsilon naught. That's a constant. Q over L is a constant. X is also a constant, and then you would have the sums of 1 over X squared plus Y squared to the 3/2 times delta Y. General, this is where you stop. I want you to be able to set up the sum, and then you can just jump to the solution. Classical, we're getting ready to integrate. Well, actually, in this case, we're getting ready to set up an integral. Solving this one requires a table of integrals, which we're not going to bother with, although I highly recommend you get comfortable with them. Okay, so to get to the analytical solution, we need to integrate. So we're going to take the limit as delta Y approaches 0 of 1 over 4 pi epsilon naught Q over L X times the sum 1 over X squared plus Y squared to the power of 3/2 times delta Y. So this is 1 over 4 pi epsilon naught Q over L X we're going to integrate from minus L over 2 to plus L over 2, the two ends of our rod. 1 over x squared plus y squared to the power of 3/2 dy. All right, so as I mentioned before, it is important for this integral that you set it up correctly. It does require a table of integrals, so if that was the case, that you were going to do an integral requiring that, I would provide this for you, or it would be something that you should know how to integrate. So you'd have to do this, or you could do Mathematica or MATLAB. That would integrate this for you. So I will just give you the solution now. So we'd have EX is equal to 1 over 4 pi epsilon naught Q over L times X. And this becomes Y over x squared times the square root of x squared plus y squared. And then we need to solve it from minus L over 2 to plus L over 2. EX is equal to 1 over 4 pi epsilon naught Q over X, x squared plus L over 2 squared. All right, so note, if done with y, EY is equal to 1 over 4 pi epsilon naught Q over L from minus L over 2 to plus L over 2 minus y over x squared plus y squared to the 3/2. You can use the same form for the table of integrals, and you'll see that EY equals 0. And you should do this on your own. But that is exactly what we would expect this to be. And so this is our expression for the electric field of a long, thin rod or a wire. And we'll generalize this in just a bit. So at this point, general, you can come back in, you'll have the result, and now you can check it. So it matches conceptually. We expected there to be 0 in Z. We expected there to be 0 in Y. And on your own, check the units. Okay, so now we can generalize this, and basically when you generalize this, all the x's become r's, because technically your wire could lie in any plane. But we derive equations with easy planes, and then we set it up to be more general. So let's examine the case when r, the distance, is much, much greater than L. So in this case, the component with r, so we'd have r times r squared plus L over 2 squared. So in the case where r is much, much bigger than L, so we're very far away from the wire, then this is approximately 1 over r times r squared plus 0, because that would get very small, which is 1 over r squared. And then this becomes 1 over 4 pi epsilon naught Q over r squared. So it acts like a point charge. So basically, if you get far away enough from anything, it's going to act like a point charge. All right, but you won't see that very often. So let's do a special case that is a little bit more common. A long rod, or like a long wire. So in this case, you would have the electric field being equal to approximately 1 over 4 pi epsilon naught. So if we look at this component here, so L would be much, much larger than the distance. So in that case, this is going to be the term that's important. This is going to get very, very small. So then you would have 2 times Q over L over R. And this works as long as you are not too far or too close to either end.